generating music using Magenta. Magenta is a library which was published by the Google Brain team. And how many of you didn't go to the talk earlier about resurrecting the dead using Python? Those who didn't. Okay, just a few. So a lot of you. Okay, so because this is actually, I think, a sort of continuation for that talk. That talk discussed how we could use recurrent neural networks to generate texts. And now I'm going to talk about the other part of the creative content, which is now music. A short intro about me. I'm Lando. I'm a software engineer at freelancer.com, and please take note that I'm neither an AI researcher or a musician. So I only took on this project because I wanted to sort of compose music, and when I saw the Magenta library, I was interested, and I started to, well, I tried to read up on music theory and machine learning, and as you will see later, I kind of failed at actually grasping the two concepts. So this is my attempt at actually trying to explain to you how I understood it, and how would you be able to use Magenta as well in your, for example, musical endeavors. Quiz, maybe? So I'm going to play 4 pieces of music, 4 clips, and I'd like you later on, at the end of the talk, to guess which of those pieces were actually generated by Magenta. So this is the first clip. This is the second clip, this is B. This is the third clip. So yeah, as you can see, they're pretty similar, and it's actually quite interesting, as we'll find out later which clip was actually generated by Magenta. So yeah, as I've said, I wanted to be able to present this to you with some sort of music theory in order for you to understand why is it actually possible for us to be able to generate music using algorithms, or specifically machine learning. And I unfortunately failed at that. I wasn't able to learn, of course, obviously, the entire body of music theory in just 1 month of preparation for this talk. But I wanted to give a shout out to this channel. It's the 12-Tone YouTube channel. I watched a lot of his clips. He actually explains a lot of concepts, a lot of theory behind music in a really entertaining way. He doodles on a music sheet. And so yeah, please check out this channel. He explains stuff like harmony, scales, and keys. So for those of you who are actually not familiar with music theory, do not have any inclination to music, music has an entire body of theory around it. For example, you could see when you read about music theory that we have these chords. For guitar players, you probably only know chords based on how your finger would land on the fretboard, or whatever that was called. But actually in piano there are chords as well, and in general there are notes that goes with certain chords, and notes which when you play with a certain chord, they don't really sound that good. So another example of a music concept is harmony. So you have notes harmonizing notes that actually dictate how music progresses throughout the piece. So for example, you're playing in an A minor key, and then you play a particular note, that would dictate whether that would actually give the listener sort of anticipation on whether or not the melody will now loop back and close to a resolution, or will it actually build up to something else. So those notes are actually dictated by the harmonic properties of the key that you are playing. And one interesting fact is that keys can even sometimes change the entire mood of a song. So you might be used to hearing, for example, a happy tone in a major key, but when a pianist plays it in a minor key, even though he's playing the right notes and he's playing the same piece in a different key, you would see that the entire piece would actually feel sadder. So major keys are happier, sort of, and minor keys are sadder tones. I'm going to play a couple of clips. Unfortunately, I can't play it directly from it. So this is an example of a guitarist who is improvising within a major pentatonic scale. So what he's doing is he's just playing around the notes within that scale. He didn't really compose this beforehand, it's an improv session. And as you can see, it sounds good. It seems like no matter what note you hit on that pentatonic scale, it just matches whatever jam track, for example, if there's a C major chord being played in the background. And then this is an example of how a key can actually change the entire mood of the song. So maybe a lot of you are familiar with For Elise. This is it. This is played in A minor. So this kind of gives you a lonely, sad tone to the song. Now he's going to play in A major. So this is For Elise, just played in a different key. And now he's going back to A minor. So as you can see, if music has these properties, these regularities, these patterns that are so well known and have been studied throughout centuries within music theory, then it should be easy for us to actually write an algorithm. Even you can write an algorithm to just generate music automatically. For example, you can just probably write a script that randomizes notes within the pentatonic scale. It could probably generate music that is not really that bad. And that actually leads us to a field of computation called computational creativity, which deals with the question of, can machines actually generate creative content? And surprisingly, this concept has been well known since the beginning of computation. So this is a code from Ada Lovelace. You probably know Ada Lovelace, who is considered one of the, I think the first programmer. This was a quote from her from 1841, and she said that, supposing, for instance, that the fundamental relations of pitched sounds in the science of harmony and of musical composition were susceptible to mathematical expressions and adaptations, then the engine, she's talking about the analytical engine, might compose elaborate and scientific pieces of music of any degree of complexity or extent. So as you can see, once we have established that music actually has a sort of mathematical theory around it, then probably yes, we could generate a program that could generate music in any genre, however complex and however elaborate it is. And there are early attempts into actually doing this. This is called a musical dice game. What this does is the composer prints notes or chords in a dice, and then he rolls it, and then whatever that is displayed on there, he just plays it. So it's it's not as bad because, as I've said earlier, as long as you are generating notes within the scale, then you're not really, the music you're generating wouldn't really be that bad. But as you can see, for those machine learning practitioners have already figured out any algorithm that we write in this way to generate any content would only be limited to the genre that we program the algorithm for. For example, in the earlier works of chess, people had to code actual chess algorithms, chess openings, and chess theories within the code, and it was only limited to chess, and you cannot use it really for Go or for any other abstract strategy games. And that's why with the recent rise in computing power, we are able to actually devise computational models that allows us to mimic human thought and be able to actually make computers learn how we learn. So neural networks, this is going to be a very hand-wavy introduction to neural networks. So for any neural network experts there, please don't judge me. So neural networks, what are neural networks? Neural networks are loosely based on how our brain or neurons specifically process information. As you can see here, you have the input layer, and then you have activated neurons. And then at the very top of the layer, you have the output layer that actually decides whether or not the thing that he sees is a cat or a dog. And this is based on how our eyes, for example, process visual information. So our eyes, probably a lot of you don't know, actually have specific neurons that only fire when they see specific lines of specific orientations. So this is a mapping of those. This is a picture of the brain and then a sort of mapping of the neurons in it. It's probably not clear, but you can. We have certain columns of neurons, and these neurons only fire for specific orientations of lines. So this is a research done in neuroscience, and they saw that when they expose a cat's brain and then they measure the neural activity of that cat, the cat's visual cortex, when they expose it to, for example, a strictly horizontal line, a vertical line, or any orientation in between, the activation of that neuron changes depending on the orientation of that line. So now we can see that we actually have very specialized neurons in our brains that then feed into other neurons that now decide whether or not you can see an edge within that picture or a shape or any other complex structures. And these neurons, we have chains of these neurons starting from the very basic neuron that detects edges to really complex structures, really complex network of neurons that actually now detect whether or not you're actually seeing a cat. So that's basically how neural networks work. It's an inspiration for our neural networks. So this is the basic model of a neural network. Let's say, for example, on your left, you have a picture of a bird. And now you process, whenever we take a neural network, what we do is we take the pixels of that image and then feed it to the layers of neurons that only activate when specific properties of that image is met. For example, if the neural network sees different colors separated by a line, then it actually probably saw an edge. Because now you're, from one color, now you've reached the edge of that particular object, and we're now traversing the next part of the image. And neurons, at the very left layer, we have neurons that directly interface with the input image, the pixels, and then they feed into several other layers of neurons that then take whatever information has been passed. For example, did the lower level neurons see an edge? Now, the higher level neurons, when they say, okay, you've seen an edge, and maybe you've seen this particular shape. And then those particular neurons then feed into higher levels of neurons that actually now decide, based on the aggregation of data from the lower level networks, whether or not it's actually seeing a bird. So now for us to be able to actually get an idea on how this learning process, this machine learning process happens using a neural network, we're trying to model the entire thing using an equation. So let's say we have x times y equals z. So x here represents our pixels, and z here represents basically the computation or the classification whether or not it actually sees a bird. So times here, I've highlighted it, it's not really your typical multiplication operator. It's a much more complicated operation that the neural network performs on y to be able to classify whether or not the x, the pixels that it sees, is a bird. So let's say the entire pixel data, we generalize it into the number 3. And then whenever we process it through the neural network, it outputs the number 6. And the neural network, when it sees that the output is greater than 6 or equal to 6, then it says, hey, it's a bird. So now you're asking, how then do we know what is y? Or how will the computer know what is y? And you might say that, hey, that's basic algebra, we just do y equals 6 divided by 3, so we get 2. But the problem is, x is not, as I've said, x is not really a simple operation. It's a very complicated operation that might not even have an inverse. So you can't really do division right in here, sort of like how you do it in algebra. So how do we now solve for y without using division? So we go back to the model, x times y equals z. And what we do, we represent the pixels as x, the classification as 6, or as z, and we try this. We move the 6 to the other side of the equation, and then we compute the difference between the prediction of the model and what we actually know. So now we are able to solve for the difference in the prediction. So how far off is our model, x times 3, from the result, which is 6. And this is what we call this the error. And now computers are really good at just plugging in values in here and trying to figure out what the y is with the least amount of error. So that's how we learn, that's how basically, in a very, very high level, how machine learning actually works. So we try to figure out or minimize the error within our models in order to come up with the actual parameters that our machine learning models will use. But what if we want to solve for x? So let's say you know that you want a bird, and you know that you already have the trained model that actually knows the parameters that it will use to actually recognize a bird. Then can we actually generate the pixels that represent a bird? And the answer is yes. So this is a simulation of how such a model will work. So as you can see, it's continuously improving the image on the left. And that's the generated image. It's not really the picture of a bird as we know it. It's more of an abstract representation of how the computer thinks what a bird is. So it's composed of features that it knows is definitely belongs to a bird. So we have, when it loops back, you can see beaks, heads, eyes within that head, and probably some feature that represents feathers. And you can probably see different orientations of that bird because the model is trained to recognize the bird, whether or not it's facing backwards, sideways, or facing in front of you. An image, this is a demo for a different machine learning project in Google called Deep Dream. So this is a regular image, and then we ask a machine learning model who was trained to recognize structures. How will it actually enhance this image? So this is what it did. It's probably not clear to you, but the model started imagining features that were not there. So in the original image, we actually do not have figures of people on the grass, but then since the model actually knows how to recognize people, it started to just imagine people in that image. So this is how we are actually, this is Deep Dream. So there's an entire collection of these images, and basically they're sort of surreal and sort of gives us an insight of what would a computer's dream look like. So this is how we're actually able to generate creative content, so to speak, based on our machine learning models. Now I'm going to talk about Magenta, the actual library that we're going to use today. Magenta is an autoencoder. So what an autoencoder is, it's sort of like a neural, it's one type of neural network, but the difference is it's actually constrained, you're constraining the representation of the image that you are using, that the model is using. By that I mean, for example, you have an image that is 1,000,000 pixels. Typically you would have a neural network that would have 1,000,000,000 neurons to actually try to generate or to learn the model of that image. But now for an autoencoder, you try to limit that number of neurons into, let's say, a couple of thousands, 100,000s, something that is significantly less than your original image. By constraining the model this way, now your neural network is now forced to pick out regularities within that image. So it cannot memorize the entire image. So if it sees a bird, it's trying to pick out the most important things to focus on. And hopefully by that way, we are able to learn the most important representation of that model. And then now we have another neural network to the right side of the latent representation that is actually trained to generate images based on that representation. So this allows us to do unsupervised learning. So we just give it an image, send it to the neural network, have the neural network just pick out the important details in that image, and then have another neural network try to mimic that, and then we compare whether or not the other neural network's prediction actually matches the original one. So if we are able to recover the original image, then probably our neural network actually learned the important properties of the image. So it's not really memorizing, it's generalizing. Magenta has two different parts. It has the visual part, the sketching, the sketch RNN, and then it has the musical part. I thought that it was easier for me to explain machine learning or neural networks using visual examples. So what about music? So we're here to talk about music. This is a slide, an animation from another Google project called WaveNet. So they're trying to learn, similar to Magenta, they're trying to generate music using wavelengths. And what they're trying to do here is taking in the speaker pole positions, and then using a neural network, they're trying to predict the next note based on first the next few notes and then a couple of notes from way back. So that way we can actually produce some kind of musical piece with some kind of coherence with it. A brief intro on recurrent neural networks. So Magenta uses recurrent neural networks, and for those who actually attended the talk earlier, recurrent neural networks actually allow neural networks to have some sort of memory. So typical neural networks can only, they typically process the information, the current information that's given. But recurrent neural networks have information on the outputs and the inputs from previous iterations of its predictions. So if those previous outputs, for example, the previous notes are relevant to the generation, then it can actually generate the next note that is sort of coherent with the previous notes. So now I'm going to play a couple of demo pieces from the network. So this is a piece that was imprinted using just one note. We just told it to go very fast. And this piece we primed it with the first formulas of the this last piece is still the same priming. The first one is. So yeah, we have interesting pieces there, but it actually doesn't stop there. Magenta recently released, well, last year they released more models. This particular improv RNN demo, now you are able to generate music that follows a certain chord progression. So previously we just had the previous model, it took the primary melody, the notes that you gave it, and then tried to continue the melody from there based on what it thought was reasonable. So now we're priming it with a note and then chord progression C, G, A minor, F, for those of you who knows guitar. Okay, so I actually made a mistake. So the ones that we're playing earlier are the improv ones. That's why they sound so good. This is the melody RNN. So this sort of sounds a bit simple, but let's play it anyways. Yeah, so it's kind of messy, it's kind of all around. But as you can see from the improv demo, we had notes that actually start to sound like a song. And now, the quiz review. Okay, so who says that it's A? Okay, I see hands that were saying that it's the third one, C. 3? C, okay. Can we actually play the clips again, A? So this is actually a more recent model that was released by Magenta. So this is performance RNN. So previously they were actually just trying to predict notes based on the previous ones. But now they started to, because musical performances are not just single notes at a time. So you have multiple notes interleaved in between and actual chords and really expressive timing. So they actually started to generate events that instead of generating notes, they start generating note start and note end. And it's actually amazing how different or actually human-like the generated music is. So yeah, if you want to use Magenta, how will you actually do it? It's just as easy as this, pip install Magenta. But if you're using Ubuntu, Magenta has a lot of, well, it has dependencies, libjackdev and libasanddev, so you might probably want to install that as well. You need this because Magenta has a MIDI interface, so you can actually plug in a keyboard and then play the notes and then feed them directly to Magenta. And then Magenta provides, so they have pre-trained models. A couple of clips I generated earlier were actually done using the pre-generated models. These models were trained from thousands of piano performances. So what I found when I was training my own model was that you cannot really throw random bunch of music that you like. For example, your entire Spotify playlist, just dump it to a MIDI file and then feed it to Magenta. It actually doesn't work that well if the genre is too broad. Because remember that Magenta, the autoencoder, will actually try to learn regularities within the input. So if your the pattern is too broad, it's too random, then autoencoders wouldn't really work that well. So try to train different models based on the genres that you want to generate. So first download, well, all of these is in their GitHub repo, so I'm just going to point out some gotchas that may stop you when you're trying to generate your own models. So first, download their pre-built or pre-trained models, and then it's the generation of the melodies as simple as improv, arm, and generate. The first, the config there is basically the what model you want to use. So improv RNN only has one model, but the melody RNN earlier had 3 models. So just read up on the Magenta repo on what those 3 models do. Basically, it has to do with how much should the model look back, or how far should it try to basically generalize. So does it look back 2 bars before to try to predict the next note, or does it just try to use the current note in order to produce the next note? Specify whatever model you want to use. And the bundle file is that MAG file, the .magenta file, is a representation of the model, basically. So whenever you train a model, Magenta tells you how to generate the MAG file, or if you downloaded one of the pre-built ones, make sure to pass in it there in the bundle. And as you can see, you can specify the primer melody. So the primer melody here, 60 represents C. So it's a Python array. So you can, a Python list, sorry. So C is 60, I think D 62, and however you want the melody to continue. And then this is the improv RNN. So I said that it's trying to generate those chords based on the chord progression, generate the melody. So make sure you specify the chord progression. So this is C, G, A minor, F. And then render chords is just whether or not it plays the chords at the background, so not just the melody. So this is a code that's been shared around in the Magenta presentations quite often. This is a quote from Brian Eno. It kind of puts into perspective where Magenta lies within this music generation or this artistic industry. So Brian Eno said that whatever now you find weird, ugly, uncomfortable, and nasty about a new medium will surely become signature. See the distortion, the jitteriness of digital video, the crappy sound of 8-bit. All of these will be cherished and emulated as soon as they can be avoided. It is the sound of failure. So much modern art is the sound of things going out of control, of a medium pushing to its limits and breaking apart. The distorted guitar is the sound of something too loud for the medium supposed to carry it. The blues singer with a cracked voice is the sound of an emotional cry too powerful for the throat that releases it. The excitement of grainy film, the bleached out black and white, is the excitement of witnessing events too momentous for the medium assigned to record them. So this is how I actually kind of agree with this code. Basically, how we want to see Magenta not as whether or not computers can generate better music than humans, or it's AI versus humans, and whether or not in the future we will just click one button and we will compose entire compositions on their own. That's kind of boring, and that's not really how we humans tend to operate. Basically, when we're given a new media, when we're given new technology, we're trying to push the limits, we're trying to break it. And by doing that, we're actually creating more avenues for more creative content. For example, the electric guitar, it was made not for how you picture it right now. It was made just to make the acoustic guitar sound louder. But then as musicians started playing with it, they actually started to see that, hey, you can actually distort this and make another kind of, an entirely different genre based on that musical instrument. So this is how I see Magenta will be used in the future. So it's not going to be the end of human creativity, so to speak. It's just going to push the limits of our creativity further using these tools in our disposal. This is Magenta. go to Magenta, the tensorflow.org for the entire thing. They actually have a cool site. They publish a lot of papers based on the research that they're doing. And their GitHub repo, please check it out as well if you want to use it. And yeah,